Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will create a new series, and today's series is about CMG CMOST. Okay, we will use CMOST. CMOST is a very good AI software within CMG applications, and it is very useful. It is very interesting. It can help us to analyze our reservoir, perform something like data analysis to predict. And by the way, we can also do history matching using CMG CMOST. Okay, and today's topic, especially I mean today's case, is about tight oil. All right, I get the data from another YouTube channel, Ahinoam Polak. So you can find the channel, and hopefully you can also learn many things from that channel. So I get the data, the tight oil case, and I want to do the analysis. I want to use CMG CMOS to perform analysis on this case. Okay, so you can see the documents tree here. You can see I have a folder called CMOST, and within the CMOST I have tight oil, and within the tight oil folder I have this data. All right, so the most important thing is not the most important thing, but we will use this one, tight oil base dot dot, and we will put this data into the builder. So we'll start from builder, and later on we will go to the CMOST. All right, so this is our simulation. This is our model. We are currently looking at the IJ two-dimensional aerial view. We can change to three-dimensional view. All right, so this is our model. I can use this rotate reservoir. It's a very, I mean, it's a simple model. It's a tight oil reservoir, and we have multi-stage horizontal fracturing here. We only have one well for this model, for this reservoir. Okay, so we go to tools, and you can find CMOS master dataset creator. Click on that. Okay, so this is CMOS definition window, and we're going to select several parameters that we will analyze using CMOS to determine is this parameter important or not for our objective value. Is this the parameter critical for our production, for example? So we are going to see the dependence of the result of our objective value on our parameters. Okay, so first we have root here, and under the root we have reservoir, hydraulic fractures. Each of these compartment has their own parameters. So first we can expand the reservoir. We have grid, array properties, and rock compressibility. Click on grid, click on array properties, and click on rock compressibility. You can see we have many parameters there. All right, so we are going to select several parameters that we will exercise on CMOS to see the importance of those parameters. So the first parameter that I want to analyze is porosity. Okay, the name is pore. The value is constant, 0.1. So click on that, click add. All right, so now we will have list of parameters in this part of window. And we can rename it. For example, I want to call it porosity, of course. And you see the value 0.1 changed to the name porosity. The default value 0.1, default value type, it's a real number. Number of parameters used, only one right now. And then we go to the next parameter. I'm going to select permeability J. Click this one and click add. I want to call it horizontal permeability, perm H, yeah, horizontal permeability, default value 0.24. It's a tight reservoir, 0.24 millidarcies, real number, and then I, okay, click I, permeability I. I want to make it double click perm H. So both perm J and perm I, they are both perm H, horizontal permeability. Okay, so it's easy. And then perm K, permeability in K direction, perm K, constant 0.06. Okay, click add. Now we will call it perm vertical permeability, so it's perm V. All right, and then the next one, I want to use rock compressibility. I want to know the importance of rock compressibility on our production. So click on this one, pressure dependence. So I will expand pressure dependence of formation porosity. Okay, it's actually compressibility. Click on that and then click add and then name it compressibility. Okay, you can call it rock compressibility, all right? But for me, I know it's compressibility. It must be rock compressibility. It's not fluid compressibility. So far, so good. And then let's close the reservoir. I want to analyze the importance of several hydraulic fracture parameters. So expand the planar fractures and the templates. Again, click on that. All right, we have several parameters here. And by the way, yeah, doesn't matter. So first, click on this. This is actually half length. Yeah. So I click on that, 55, click add, and I call it half length. Okay. So I want to know the importance of my half length. And the next one, I want to know this one. Okay, by the way, I changed the resolution a little bit so that you can see the whole window. All right, so here we have WF1. It's actually the permeability of the fracture permeability. So I click on this one and then I will click add and I call it fracture permeability. Okay, fracture perm. And then it's also important, this one, layers up. So how many layers I want to extend my fracture to. So I will, for example, 3, I want to extend my fracture to 3 layers up. And then I also have layers down. So I want to extend my fracture to 2 layers down. Okay. So I click this one and then click add. And we can call it, for example, layer or fracture underscore layer underscore up. All right, and also this one, let's call it fracture underscore no layer down. Okay, so far so good. So we have 8 parameters so far. And this one is not really important. And let's go to the rock fluid, rock type 1. And we have this one. Right. Actually, not rock fluid, but builder keywords. I want to find my relative permeability table. So let's expand the relative permeability table, rock type 1. We have set 1 here, expand again, and show data. So we have several values. You can go to the right side. We have several values, and I also want to do analysis study on several of these values, like this one. Now you see here, KROCW 0.81. I want to study on that. Let's call it KROCW, KROCW, okay. And actually based on the letters here, it's oil relative permeability at Conat water saturation. CW, Conat water saturation, right? KRO, it's oil relative permeability or relative permeability to oil. And the next value is this one. Now it's KRGCL. It's relative permeability to gas for gas liquid system. All right. So click add. Let's call it KRGCL. And the next one here, 0.15 SORG. It's a residual oil saturation for oil gas system. Click on that. Let's call it SORG. Beautiful. And let's go to the right side. This one, 0.04, it's SG crit, is critical gas saturation. The saturation at which the gas starts to flow. Click on that and let's call it SG crit. Okay. And we have SORG, SG crit. Now we have 12 parameters. Okay, so far so good. I want to do my study using these 12 parameters. But wait, I also actually want to do analysis on this value, NOG. So it's the curvature of the relative permeability for oil gas system. So I click on that. Let's call it NOG. Okay, so there. And then I want to make sure here, the NG 2.3. Click on that and rename it to NG. Okay, so I have 14 parameters from which I want to do analysis. I want to know the dependence of my oil production, for example, the dependence of my oil production on each of these parameters. I want to know the importance, the criticality of these parameters. All right, so far so good. So from here, we can click OK. Be careful here. The current CMOST master dataset was modified. Do you want to save changes? Yes, of course. And again, be careful. Some CMOS parameters will be lost if the window is closed. Modify some parameters and open this window again. Do you want to close the window? Sure. All right. So, yep, we are done here. So let's set aside our builder first. And now here we have a new file with .cmm there. Okay, .cmm there. And yeah, it's a new file created for our CMOST exercise. Okay, so from builder, now let's open the CMOST, intelligent optimization. Yeah, that's CMOST AI. Hopefully we can learn many things, many interesting things here. Click new project and let's call it Tide Oil. All right. And then we will use the base dataset. So click on browse. Okay, so for the base dataset, we will use this one, Tide Oil base .dat. Okay, so we will use .dat file. All right, so from here we can click OK. Now we will create a new study. Click on new study and then rename the study to, for example, Tide Oil sensitivity, like this. And then again, we will use base dataset, browse. All right, and then use this Tide Oil base. Click on open, click OK. All right, so now we have here Tide Oil sensitivity analysis. Click on this one. Now we have several features here. And input, control center, results analysis, many important things here. So we will take a step back first. All right, I want to create a new study. So in that new study, I want to upload my production file as well. So here we can exclude it first. Sorry for that. New study, let's call it Tide Oil. And for the type, be careful here, sensitivity analysis. And browse, again, I will use that. Click OK. All right, so now we will do here the Tide Oil, the sensitivity analysis on this one. Double click on Tide Oil. So we have again input, control center, results analysis. Let's go to input first, general properties. Okay, so for master dataset, relative path here, Tide Oil.cmm, and base dataset relative path will go to Tide Oil base dat. And here, I want to import field history production file. And yeah, later on we can do history matching to compare the simulation results with the actual production data, actual historical data. So click import this one. And you can see we have two files, the pressure data as well as the production data .fhf. Click open. All right. So now we have these two files. The simulator, we will use IMAX. We can use IMAX for Tide Oil with horizontal well and hydraulic fracturing. And let's check fundamental data, original time series, user-defined time series, property versus distance series. We'll not cover it for this series, but later on, hopefully in the future, we can talk about this. Parameterization, objective function. All right. So here, we will start from here. expanded parameters. So here we will import some of the parameters that we have selected previously in the builder. So we click import. Okay. There are no new parameters to import. All right, so let's be careful here. We will erase this first. Okay, and then we will create a new project. No. All right, so, or maybe we can close this one first. And let's delete this one. Okay, so be careful which file we want to use as dataset. That's very important. The selection of the dataset, that's very important. So I will go back to my builder first. This one, I want to make sure that I save it. Okay, so if we go to tools again, CMOS master dataset creator, I have these selected parameters. Okay, so I've checked my builder again, and let's go back to CMOST. Let's expand the window, create new project. Let's call it tight oil, and then base dataset, browse tight oil. We will use this one. By the way, if you change to all files, you see we have tight oil base CMM here. I'm going to select this one. So we have updated this tight oil base dot with the selected parameters. Click open. Click OK. And then let's create new study again. Let's call it tight oil sensitivity or analysis here. And then type sensitivity analysis. And again, the base dataset. Okay, so click on browse. Click this one, click open. Sensitivity analysis, okay. Okay, tight oil. Double click on that. General properties. Here, browse. Let's select this one. Okay, the first CMM file that we have created. Click open. And this file does not exist in the project directory. Would you like to copy the file to the project folder? Yes. Okay, be careful here because this one only contains the selected parameters. All right, and base dataset relative permeability, okay. And let's again import the production files. Click open there. So let's go to parameterization, parameters, click import. Importing operation was successful. So the first thing that we do wrongly is this one. So if you go back to the previous period of this video, I missed this one. So I just go and use whatever I have initially in this section .cmm. But that new CMM file does not contain the selected parameters, does not contain this selection of 14 parameters. Okay, so I go back, I call, browse, and I take this one. Okay, I take this one, and then the CMOS will copy that database here into this folder or into this trajectory. Yeah, this file. Okay, directory, I mean, not trajectory, directory. So far, so good. So parameters. So now we have 14 parameters successfully. And let's go to the top first. What do we have here? Compressibility, name, comment. If you want to type any comment here, it's active. Default value is 1.5 to the power of -6, and it's continuous and real number. Okay, and then you can do modification here. We have a lower limit, upper limit, we have discrete sampling settings. Okay, and then the distribution. Currently, by default, it's unspecified. Okay, so it's uniform. I mean, there is no specific distribution. By the way, you can change it to deterministic distribution, or if you are quite certain that compressibility exhibits normal distribution, then CMOS will give you just that. All right, let's go back to unspecified. Again, I'm going to review these selected parameters. So I want to know the importance of these 14 parameters. I want to know how important is compressibility, fracture permeability, the layers extension, up and down, the half length of the fracture, and then the relative permeability parameters, horizontal permeability, vertical permeability, and then porosity, and so on and so forth. By the way, you can add another parameter or other parameters if you want. So do I want to add that? Yeah, just I'm just going to demonstrate that. So we can go back and then we can add another parameter. For example, we can go to the builder again. Okay, so if I want to add another parameter, for example, we can go back to builder, click on this button, builder. We'll call the builder again, and we meet with this window again. For example, we can click grid, for example, grid, array properties, pinch out properties, for example. Okay, you can click this one. All right, and then you can click on this add button again, and we will have the 15th parameter, which is the pinch out array. All right, and again, you will click OK, and then you will save the update and so on and so forth. And you also need to overwrite the CMM file. Okay, so maybe, yeah, let's just do that. This exercise, this just detour exercise will add a little bit of complexity, but it worth taking. So I click on add, and let's call it pinch out. Click OK. And the current CMOST master dataset was modified. Do you want to save the changes? Yes. And again, do you want to override it? Click yes. Builder will be closed. If you close this window, do you want to proceed? Of course. All right. So, yep, click import again. Importing operation was successful. Now we have the 15th parameter, which is the pinch out array. So far, so good. So I just show you that missing one or two parameters in the builder section, it's not the end of the day. Okay, you can update the selection of the parameters even here in this CMOST. Okay, so we can go back to this one. First, for example, fracture layer down. Default value 2, or yeah, 2 layers extension down when we do the fracturing, and the source continuous real, but number of layers, it's actually discrete integer. Okay, the number of the layers, it must be discrete integer number. Okay, so the visualization changed to this one, integer value and prior probability. So click on insert or delete, generate. So method, arithmetic sequence. Okay, so minimum value 0, 0 layers down, maximum value, for example, 4, and number of values 5. Okay, with the same probabilities. Okay, 0 0.2, 0 0.2, 0 0.2. Click OK. All right. And then, for example, the fracture layer up, it's also discrete integer, of course. And then we click on the generate, minimum value 0, maximum value 3. Okay. Number of values 4. All right. And for example, the half length. So the default value is 55, lower limit 41.25, upper limit 68.75. Number of discrete levels 11. So let's say it's 20. Let's change it to 20. And then the next value is the 90. Okay. And then the horizontal permeability, can change it to 0.01 and 0.4, the upper limit. Okay, by the way, you can always change to a specific distribution if you know, but yeah, you can use unspecified. And then for the vertical permeability, now let's be careful here. So go to source. Instead of continuous real number, I'm going to use formula, and automatically we will find this text editor. Okay, and yep, I'm going to calculate my vertical permeability based on horizontal permeability and kV per kH ratio, or permeability anisotropy. So we can click this one or type in this one, perm H multiplied by kV kH ratio. Okay, kV kH ratio is the permeability anisotropy. All right, so that's the formula to calculate the vertical permeability. So we are going to add a new parameter, insert, let's call it kV kH ratio. Make sure the name is the same with what you type in. All right, kV kH ratio, and default value 0.25, lower limit 0.05, and the maximum 0.5. Again, 11 unspecified. And let's check the fracture permeability. 20,000, you can change it to 2,000, up to 30,000 millidarcies, unspecified. Okay, so yeah, fracture layer down, fracture layer up, fracture permeability, horizontal permeability, vertical permeability, using formula, of course, kV/kH ratio or permeability anisotropy. And the next one is porosity, default value 0.1, We can use these limits 0.075 and 0.125 unspecified, and an OG 2.3. We can change it to 2 and 2 point or 3.5 instead. And yep, so far so good. Make sure you save when you do important update. All right. And the next thing that we want to do is we go to the objective functions. Now it gets more and more important, and basic simulation results. Okay, you can see basic simulation result from original time series, basic simulation result from user defined, or characteristic time durations. We want to do analysis on this section and click on this one. First, for example, I want to know the cumulative oil production, and the next thing that I want to assess is the impact of those 14 or 15 parameters on my cumulative gas production, and lastly to my gas oil ratio. Okay, so this one, click on this property and you can select the result that you want to analyze. For example, this one I want to study for the cumulative oil production. I will call it NP. Okay, that's the symbol for the cumulative oil production. Characteristic time, base case stop, origin type, wells, and the origin name, this one, this file, horizontal well for well number 1. And the next one is the cumulative gas production. And usually the symbol or the index for cumulative gas production, I'm not sure about that, but I think it's GP. Okay, it's cumulative gas production, and let's open this property, cumulative gas production. SC is the standard condition. And lastly, I want to check the gas oil ratio standard condition, call it GOR. Okay, so I want to study the impact of my 14 or 15 parameters on my cumulative oil production, cumulative gas production, and gas oil ratio. And then parameterization again, pre-simulation comments. So click on this one. We want to run CMG Builder silently. So when we perform the analysis using CMOS, we actually run the simulation within the builder, okay, using the builder. So I will run CMG Builder silently there, okay, and builder executable path, this one. Okay, and that's it. We go to the next one for the control center. Later on, we will play using this section, using this window. We will use this button. So yeah, you can just check this window first. CMOS AI engine, the engine name, response surface methodology, and this is the engine surface. I mean the engine version, status new, experiment progress. We will observe the progression of our experiment. Later on, using this chart, status and result, status summary, expecting and reuse pending, result summary, waiting to be reprocessed or unknown. And we will also see some notes here in the engine events section. So continue to engine settings. Okay, We are just going to check it. Autosave result interval, user specified random, acceptable R square, yeah, 0.85, acceptable R square adjusted, acceptable R square prediction. You can adjust these values, okay, as per the accuracy that you want, the level of the detail that you want for your experiment. Let's continue to simulation settings. So schedulers connected using schedulers in launcher. Please do not close launcher when the study is running. Okay, do not close your launcher. So we have we have two scheduler, CMG Cloud, if you want to perform on the cloud, local. I prefer running on my local computer, and max concurrent jobs. Let's change it to 4. Okay, max failed jobs 25, work plan all time, job priority low. You can leave other as per default. We will use IMAX, okay, simulator version, and number of cores, one, I mean, and cloud node type, this one, maximum runtime per job. I don't want it to be too long, so let's change it just to 1 hour. Okay, number of cores per local, I select 1, maximum running time, only 1 hour. Okay, and then experiment table, you see we still have error note there. Okay, ID 0, generator reuse. We have note here, waiting to be reprocessed, proxy role ignore. Okay, here we will click this one, resolve reuse pending, resolve selected experiments. Okay, KVKH 0.25. You can scroll to the left or to the right to change the value. And we have the lower limit as well as the upper limit. So click on OK. And you see now we have no longer error sign here in experiment table. All right, so far so good. Let's check again. This one we have error node. Oh, there, it's still empty. So change it to here and change it to here. Perfect. So go to control center and then let's check. I think we are good. So we can click on this one. Please wait. Okay. Local. And then maximum concurrent jobs 4. All right, click OK. Okay, still running. And yeah, it takes some time. Currently, we are still validating input data, reprocessing experiment, creating initial experiment. Okay. Engine started with seed. And you see the colors change here. It's great. Job type oil sensitivity analysis is submitted to local. Start pre-simulation command. Still 44 seconds. It takes some time. Maybe it takes 20, 30 minutes. Of course, it depends also on your computer, the processor. Job type oil sensitivity analysis number 3 is submitted to local, and then my computer, the CMG will run the simulation. So I think I'm going to stop the recording. Okay, and then I will see you later after the computation is completed. Okay, so thank you and see you later. So we continue our learning on CMG CMOST, and in previous sections we have constructed the sensitivity analysis, and then we we check at the control center, and we see that the experiments were on progress, and then we stop the section, and as you can see we have completed the experiments, and you check at this one elapsed time. It takes 21 minutes 40 seconds to complete all the experiments, and you see the engine events here show all. You can check the note, job tight oil number 79, and so on and so forth, complete launcher, and then start pre-simulation command, and so on and so forth. And you can also check the experiments table here, proxy role, training, you see, and we go to the right at compressibility, this value, at that fracture permeability, fracture layer down, fracture layer up, the combination of all these parameters. So overall, we have how many? 93 or 92 experiments here. All of them are completed. Okay, result status. Some have the normal termination, but some abnormal termination. All right. And again, we do this sensitivity analysis, we do this experiment to know which parameter is really, really important for cumulative oil production, cumulative gas production, gas oil ratio, and which parameters that are not very important to influence that objective functions. Okay, the objective functions, the objective value that we want to know is, of course, the cumulative oil production, cumulative gas production, and gas oil ratio. All right, so we go back to the control center. Status complete, and this light green reused. We achieve 92% completed. And the result, 67 normal termination and 26 abnormal termination. You can check it also here, status summary and result summary. All right, so far so good. And then from control center, we can go to parameters. By the way, under the result and analysis, we have parameters, and then the time series, property versus distance, objective function. Okay, and we can expand the parameters. And yeah, you can see we have run progress, histograms, all experiments, histograms, filter experiments, and also the cross plot. We check the run progress, and we have all our parameters that we insert in our experiment. So let's check the first one, compressibility. So this is the, yeah, you can say the, yeah, the value of compressibility that we use. And you see, we have a random number, random selection of compressibility. Sometimes big, sometimes small, sometimes big, sometimes at the middle. Yeah, we pick the compressibility value that we put into our experiment. We take it randomly. All right. And also the fracture permeability. You can also check the value, by the way. The x-axis, the horizontal axis, is the experiment ID, experiment number 1, experiment number 2, all the way to experiment number 92. And yeah, fracture permeability. This is the random selection, fracture layer down, fracture layer up. You see, we select discrete number, okay, for fracture layer up. So we don't have 1.5, 1.25, 1.3. We only have 1, 2, 3. We have integer for fracture layer up and fracture layer down, okay? Because in fracture layer up and fracture layer down, we are talking about how many layers that our fracture will extend to, okay? And we only have 1 layer, 2 layer, 3 layer, 4 layer, discrete, okay? Half length, okay? Relative permeability to oil. This is the curvature, horizontal permeability, vertical permeability, KVKH, porosity. All right, so these are, again, these are the values for each parameters that were selected to be used in our experiment. That's for the run progress. And we go to the next section. I will close this one and then let's open the histogram. Okay, the frequency now, compressibility, the horizontal axis, the for the each parameter, and the vertical axis, the frequency. For the compressibility, fracture permeability, layer down, layer up, half length, and so on and so forth. All right, maybe all of these visualizations, yeah, maybe it's not that we won't ultimately, but of course, because we are doing experiment, we want to know. We want to know the histogram, we want to know the run progress. But yeah, again, although this is not the final product that we want from our experiment, these are still important for us. The frequency, the histogram, right? Okay. So I will just go through and show the histogram for all of us. Okay, for the all experiments and also for the filter experiments. All right. Cross plot. Yeah, for we need to do the operation, but I will skip it for now. And another thing that's very important and interesting is time series, observer. Okay. Now, now this section is very, very important. The horizontal axis is the time, okay, the production time, and the vertical axis is the objective function that we want. And this one is the cumulative gas produced standard condition. And you see the legend. This one is the general solution. Okay, all the solutions that we generate from our experiment. And the black line is the base case. We have the base case from our builder, right? And this one, these blue dots are the field history. So by doing this, we are actually doing history matching at the same time. Okay, but that's another story for another day. We will focus on history matching using CMOST. But right now, I just want to know what's the influence of each parameter, permeability, porosity, and so on and so forth, to my cumulative gas production, and what's the influence of the combination of these parameters to my production. And you see from here, okay, if I zoom in, a certain combination of my parameters produces a result, a solution that is almost matched with my field history. Okay, so those combinations, those values of the parameters, maybe they are the correct solution that will mimic, that will match the field history. But again, that's another story for another day. So time series is very important. And now for the cumulative oil production, the first one is for the cumulative gas production. And yeah, the cumulative oil production. And now it's for the gas oil ratio. Interesting. Okay, and I will close the time series and parameters, property versus distance. Okay, let's keep it for now. And objective functions. Okay, let's expand this one. We also have run progress, histogram, crossplot, and proxy analysis. And proxy analysis is very important. Run progress, expand. NP is cumulative oil production. Okay, so this shows the cumulative oil production that we generate from each experiment. Sometimes small, sometimes big, sometimes between big and small. So we can see the range that we have, that we get from the combination of our parameters. And again, and you remember that for each parameter, we have upper limit and lower limit, right? And for the GP, cumulative gas production, this is what we have. And for GOR, gas oil ratio, this is what we get. Still, under the objective functions, histogram. Okay, so yeah, this is getting more and more important. So now we have the frequency on the left vertical axis. On the horizontal axis, we have cumulative oil production. And on the right axis, right vertical axis, we have the cumulative probability. So now we can get estimation for P90, for P10, for P50 using this histogram objective functions, right? For cumulative gas production, gas oil ratio, it's very, very important and interesting. Cross plot. Okay, now we have property versus distance, but we skip that. I want to focus on cross plot. We can click on this operation, select. Okay, and we can select each of these parameter to know the influence to our objective function. Okay, so for example, I want to know the influence of my horizontal permeability and the cumulative oil production as the objective function, the parameter from H. All right, beautiful. So now I know that if we increase if we have higher horizontal permeability, then generally we will have higher cumulative oil production. Okay. And this one, NP versus NP, it's not important. So how about this? This one, compressibility versus cumulative oil production, almost no, almost no influence. Fracture permeability, generally as we increase the fracture permeability, we will get higher cumulative oil production. We can set the plotting here. I can have two plots horizontally and two plots vertically. So I will have 4 plots. Okay, and this is for the setting for the page. Okay, and I can switch to page 1 and page 2. Interesting. You can again click on this button and change whatever you like. So for example, let's focus on the half length against the cumulative oil production. Okay, because I just want to know one parameter, so vertically only one. I can say that, yeah, generally, if we increase the half length, we will get higher oil production. Okay, so yeah, by knowing this, you can design the fracturing design accordingly in such a way that you will get longer half length. Okay, you can design your fracturing job in such a way that you will get longer half length in your tight reservoir. Okay, and what else? Fracture permeability, of course. Yeah, I want to know KV/KH ratio on cumulative oil production. All right. So for this tight reservoir, if you increase your vertical permeability by increasing the KV/KH ratio, you will get higher cumulative oil production. But of course, KV/KH ratio is given. It's the property of your reservoir. You cannot increase the KV/KH ratio, right? I'm just saying that if the KV/KH ratio is higher or your vertical permeability is higher, for this model, for this reservoir, generally you will get more oil. Okay. All right. And then, yeah, you can also do cross plotting for GP and for GOR, of course, right? And what else? Proxy analysis. Now it's very important. NP. Okay, the first one, model QC. Wow. I think it's one of the most important for all this analysis, by the way, the proxy analysis. So you see the proxy predicted NP, cumulative oil production, on the horizontal axis, and the simulated NP on the vertical axis. You see this 45-degree line, the blue line, right? And the dash line, blue dash line, 55, 95 confidence curve, this trend, I mean this one, and that one. And training experiment, of course, by the CMOS is actually data analysis and sort of machine learning software. So we have training and we have verification. We have training experiment, we have verification experiment. And you see, we get relatively good result. So here, proxy model info, reduce simple quadratic, alpha 0.1, the R square for training 0.932, it's good, right? And the R square for verification 0.926, it's good. Okay, so you see, on the on one hand we have simulation, the result, the vertical axis, and on the other hand we have proxy model, which is sort of the machine learning version or regression version that is constructed from all of this experiment. So we have proxy model and we have simulation, and you see proxy model can sort of mimic the simulation result. So as a result, consequently, we can use the proxy model because proxy model will help us to predict in more quickly, right? Predict more quickly, so you can get the model, the equation from the proxy model to get the objective function to know to predict the cumulative oil production without doing the simulation. Because of course, doing the simulation takes time. Okay, it needs more concentration, more dedication. It is far more, far simpler if you use the proxy model. Okay, but of course you need to use the proxy equation in the limit that you use in the experiment. Okay, and we can also check in more detail the quality of the proxy model. Check it from the statistics, the R square, good, R square adjusted, R square prediction, good, mean of response, standard error, analysis of variance, okay, and then the effect screening using normalized parameters. And this one, the coefficient in terms of actual parameters. Okay, so yeah, this is quite funny. So this is maybe I can say one of the most important thing using CMOS is this equation. So instead of using the simulation, instead of running the simulation, I can use this equation to predict instantly the cumulative oil production using this equation and the data that I have. So if I know the fracture permeability, if I know the layer down, layer up, if I know the KVKH, if I know the half length, I can predict instantly the cumulative oil production without needing to running the simulation. It's great, right? It's great. And effect estimates. It's also another thing that's very important. We have the parameter, and I'm focusing on the NP. I can also do that for the GP, by the way, but let's focus on the NP. So NP. So as you can see, we have the maximum and we have minimum, but the most important thing is this one, the parameters. So as you can see, perm H indicates the longest bar horizontally. So it means the most important parameter that will govern my cumulative oil production is the horizontal permeability. And it influences the cumulative oil production positively. So if you have higher permeability, greater horizontal permeability, generally you will get more oil. KVKH also, but you see the pinch out, the relative permeability of oil at Conant water condition, and the NOG, generally they are not very important. Fracture permeability, of course, it's quite important. It gets the third rank, and then fourth rank, they pinch out multiplied by pinch out, but of course that's not, I don't know what pinch out multiplied by pinch out, by the way. KVKH ratio, and then half length, quite important, but not as important as the perm H. Yeah, you see, interesting, right? So I think this is another thing that you want to get ultimately from CMOS. So if you run CMOS, you actually want to get this equation, and you also want to get this visualization. And then Morris analysis, it shows us which parameter actually is the most important. So again, here, perm H. Again, the horizontal permeability is the greatest, give the greatest influence determining our NP. For GP, let's check the Morris analysis. Again, the perm H. And for GOR, Morris analysis, nothing very special influencing the GOR. But still, perm H, more important. Porosity gives negative effect on the GOR. So it means that if you have greater porosity, you will actually have less GOR. Okay, go back to NP, Sobol analysis. Wow, it's another thing that's very important, the parameter and the effect. Okay, the main effect, the green one, and this one for the interaction. You see, 58% influence actually comes from horizontal permeability, and the next one is fracture permeability, and then KV/KH ratio, and then half length, and so on and so forth. So, you know, although it's a tight reservoir, still, if you have greater permeability, generally you will get more oil. All right, and the proxy setting, you know, the proxy model type, polynomial regression. You can also do neural network if you want, but I think it's a story for another day. Polynomial model type, find max R square adjusted. Yeah, that's what we want, because high R square, it means good correlation. Exclude statistically insignificant terms. Yes. Significance probability alpha 0.1. Yeah, generally we use that. And then let's go back to control center, proxy dashboard, proxy model generation. We can have polynomial regression, RBF, neural network, objective function proxy, and then let's expand this section. Okay, this one, the experiment, you know, yeah, this is the experiment number 1 down to 92, the value, you know, for the compressibility, for the fracture permeability, and so on and so forth. Proxy role as training or as verification, and generator, we use response surface methodology. And again, experiment ID, if we change it to experiment number 12, we have another combination. Okay. All right, so proxy model generation, polynomial regression, and then click on this button. The proxy model is ready for prediction. Okay. Build, and then RBF neural network. Press on that. The proxy model is ready for prediction. Okay. Beautiful. And then objective function proxy. Click on that. All right. So we perform polynomial regression, we perform neural network, and we also perform the objective function proxy. Let's check if we can. Yeah, the first one is the fundamental data series plot. And this one is the objective function data, the name, the objective function, cumulative oil, cumulative gas, GOR, QC simulation, QC polynomial, QC RBF, what if polynomial, sorry, and what if RBF, and go to fundamental data series plot. This one, open, click on select, and then for the SR3 time series, okay, for each the objective function, cumulative gas, cumulative oil, gas oil ratio. All right, click on OK. And yeah, you know, let's check the plot, the black line. Let's focus on that first. So this is the black line. This is the tight oil sensitivity analysis number 12. Okay. I can change to another ID. All right. Let's go to the first one. And then the polynomial regression for the ID1. This is the first method using the polynomial and using RBF neural network. It matches perfectly, all right? And polynomial regression, but using what if scenario, it matches the polynomial regression, and RBF neural network what if scenario, it matches the RBF neural network. But what about the field history? This one. So let's go to, you know, yeah, you can change it manually like this. Okay. And plots on horizontal. We can get this one for the cumulative gas, cumulative oil, and cumulative, gas oil ratio. And yeah, you can also check it. This one, vertical 2. Okay. So you can, you can check one by one the your experiment. Now, let's check the experiment. Yeah. So like this. All right. Yeah, you can do it. You can check one by one to know which parameter will give you the closest prediction to the field history. But actually, that's a subject for history matching. But doing this CMOS analysis, it's not necessarily about history matching. Okay, it's actually about sensitive analysis. All right, which parameter and which combination that will give you the highest cumulative oil production. And you can do that using polynomial regression. You can also do that using neural network, and then you compare the result from polynomial regression and the neural network. Also with this what if scenario, right? Okay. And by the way, for the what if scenario, you can adjust like this one to get, yeah, if you are doing the history matching, you can adjust this one in such a way that you can match the prediction with the history data. Okay. Porosity. Yeah, but basically you create another experiment, right? Like this. Okay. So, oh, I think it's good. Yeah, it's good. So actually I almost match the experiment with the history. field history data. But again, let's focus on that on another video, another series. By the way, we have completed our sensitivity analysis using CMOS. So if you follow me from the beginning, you right now maybe already understand the powerfulness or the power of this software, right? It helps us to do sensitivity analysis. It helps us to do the data analysis and to compare it with the simulation. And again, what you actually want to get from this exercise is actually the proxy analysis, the result in terms of the equation and the visualization of how important is this parameter and how important is the combination of those parameters. All right, so I think we can call it a day. Thank you so much for watching. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching again and see you again in the next CMG or CMG CMOS videos. Thank you.